Hello and welcome to chapter 1. So in chapter 1, we are going to discuss about the 5G air interface, its use cases, spectrum utilization, numerology, resource grid, and the introduction to physical channels and signal as we described in the last chapter. So let's get started. So I'm sure you guys are already aware of this slide. These are the different use cases of 5G. So 5G from the very beginning has been divided into three major parts. So if you want to know about network slicing, so in network slicing also there is a slice service type, which basically differentiate a 5G network in these three major use cases. So in simple words, if I have to explain you that the 5G in future or 5G network is going to cater these three different types of use cases. One is called as eMBB, another one is called as URLLC, and then we have massive machine type communication. We have discussed in detail about this different use cases in a training program called 5G End-to-End Essentials. So I don't want to give more focus on this as of now. If you want more detail on this, you can please refer to our previous training called 5G End-to-End Essentials. Let's get started. All right. So next is the operating bands in which 5G is going to work. So 5G operating bands are divided into two frequency ranges, FR1 and FR2. FR1 is the same traditional frequency bands like which all supports in our previous GSM 900 and 3G and 4G. So all those spectrums from the previous as well as new 5G spectrums will be available here. Then we have millimeter wave range, which are from the FR2. So they are high frequency bands with extreme high bandwidth, which are going to be available. So 5G is more or less going to operate in these frequency bands only. Now we will talk about the resource grid of 5G. So before we understand a resource grid of 5G, let me now go a little slow because the other two are the part of the basics, so that is clear. Now let me explain you about what exactly is 5G resources, right? So let me start with the very basics, right? To understand resources in any of the telecom network, we have got two domains to understand. One is the frequency domain and the other one is the time domain. So in this particular chapter, we will discuss about both the things. I'm sure you guys are aware that 5G is also based on the OFDM a type of multiplexing scheme, multiple access scheme, something similar to what we used to have it in LT, right? So in OFDM symbols, what happens is we divide the overall spectrum into small subcarriers, and the smallest subcarrier will basically considered as one OFDMA symbol. So for example, in case of LT, the smallest symbol was 15 kilohertz. So smallest symbol means this 15 kilohertz resource element or subcarrier or OFDM symbols. So they are the same thing, resource element, OFDM symbols, or you can call it as subcarrier. So they are same thing. This is the smallest unit. The meaning of smallest unit is that this is the smallest granularity where the data is going to flow. If you are using a QPSK modulation, this symbol can carry 2 bits. If you will be using 16 QAM, this symbol can carry 4 bits. If you will be using 64 QAM, this symbol can carry 6 bits. For 256, this symbol can carry 8 bits. So this is how the smallest symbol means. But in case of 5G, we have a concept called numerology. So what is the meaning of numerology? So this, I think, is a good image which will explain everything. So I've, taken this table from the references from 3GPP specification 38.300. So this is basically the meaning of numerology. So what does that signify? It signifies that the smallest symbol is not fixed to 15 kilohertz like we used to have it in LT, but you can have a different subcarrier spacings which you can choose from, and that is defined by its numerology. So we have a formula called 2 to the power of mu times 15 kilohertz is going to be our subcarrier spacing. So let us take the example. Let us take this through an example from the Excel itself, right? So we have numerologies, which is considered as mu. So numerology could be defined as 0, 1, 2, 3, and 4. So 5 numerologies are possible, and we have subcarrier spacing like this. So our subcarrier spacing could be 2 to the power of mu times 15 kilohertz, right? So let me put it into a formula. So for example, 2 to the power of mu times 15 kilohertz. So 2 to the power of 0 is 1. Anything raised to the power 0 is 1. So these are different subcarrier spacings which are available. So we got 15 kilohertz subcarrier spacing, 30 kilohertz subcarrier spacing, 60 kilohertz subcarrier spacing, 120 and 240. Now, what is the significance of these different subcarrier spacings? If you know what is the meaning of subcarrier spacing, which I explained you just few minutes ago, this is the smallest unit which can carry the data. That means 15 kilohertz is also going to carry 2 bits when you will be using QPSK modulation. 30 kilohertz will also be carrying 2 bits if you are using QPSK modulation. Same is the case with 60, same is the case with 120, same is the case with 240. That means all these subcarrier spacings are going to carry equal amount of data. So you are using, but the only difference is you are using a bigger bandwidth. So what does it signify? It signifies that since the frequency is bigger, its time domain space will become smaller. So if, okay, let me explain you what is time domain now. I hope you are understanding. So we know a very old theorem that time is equals to 1 by frequency. If I say my frequency is 15 kilohertz, so the time taken to carry the data from 15 kilohertz will be 1 by 15 kilohertz, which will be equals to 66.67 microseconds. I hope you guys are aware of this. Now what happens is, so in frequency domain, the size of the subcarrier is 15 kilohertz. In time domain, the useful symbol duration, right? Useful symbol duration is 66.67 microseconds. But what happens is, to override multipath fading, to overcome the issue of intersymbol interference, which happens due to multipath propagation, we add an extra time which is called as the guard period, right? Normal cyclic prefix or extended cyclic prefix. These are the guard times which are added in this useful time in order to make it successful, right? So what happens is, my useful symbol duration is 66.67 microseconds. I am going to add 4.76 microseconds, and now my overall duration, symbol duration, will become 66.67 plus 4.76 microsecond, which is 71.43 something microseconds. So this becomes the useful duration, this becomes the overall duration of the symbol. Now let me explain you one more time. So in this case, the frequency domain space is 15 kilohertz, and the time domain space of one symbol is 71.43 microseconds, something like this, which is a summation of 66.67 plus 4.76 microseconds. So now coming back to our example, what is happening here is, when you increase the subcarrier spacing from 15 to 30 kilohertz, your symbol duration from 71.43 microsecond will just remain half. And the same thing will happen when you move to 60, it will just remain half of that. And for when you move to 120, it keeps on reducing the time, right? That means to carry 2 bits of information, now I will just spend 4.46 microseconds. Previously, I was spending 71.43 microsecond. This fundamental is very, very important, guys. So if you remember, I just explained you, we have URLLC type services, ultra reliable services, which requires very minimal latencies, right? There the throughput is not a big issue, but the latency is very important, because you'll be driving in an autonomous car which is driving on its own. So how quickly you will make the decision will be a very important role in order to make URLLC type services into a reality. Therefore, we need to make use of different types of numerologies or different types of subcarrier spacing. But on the other hand, the problem with this is that you are actually utilizing a bigger part of the spectrum to transmit actually the same amount of information which you could have been transmitting with the smaller frequency as well, right? So this is going to, in a way, going to add a little overheads in your network, but everything comes at the cost of improving the overall functionalities. So for URLLC type services, we could be using higher frequencies of subcarrier spacing. For EMBB type services, where the throughput is the most important thing, we are going to be using same 15 kilohertz as the subcarrier spacing. Okay. So now we are clear with this. Then next thing is physical resource block bandwidth. What does that mean? So this means physical resource block is nothing but a bundle of subcarrier spacings put together, right? So one subcarrier or one resource element or one OFDM symbol has the capabilities only to carry 2 bit, 4 bits, 6 bits, or 8 bits of information as of now. Now what will happen is that that means it is too small for the scheduler to allocate them to a given user. So what we do is we don't give the allocation on the resource element, but we give a bundle of resource elements put together, which are considered as one physical resource block. So the calculation is very simple. One PRB or a physical resource block is nothing but a combination of 12 resource elements. You can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So these 12, every one of them is actually one OFDM symbol or resource element or subcarrier, right? So a dozen of resource elements put together is called as one resource block. To make you understand even better, this resource block, you can consider it like, for example, how it would be like if you are working in a company and you start asking for hourly salary. That means you work for 1 hour and you go and ask for your salary. You work for another hour, you go and ask for another salary. So it is going to put a lot of load on the scheduler who is giving you your salary. So therefore they have decided, okay, we will not give you hourly, we'll give you for 1 month. Like in some countries, they have weekly salaries also, right? Like in New Zealand, etc. So they work for Monday to Friday and then they get a part of their salary on every Friday so they can enjoy the weekend. Okay, coming back. So coming back, physical resource block bandwidth. So 15 times 12 is 180. We will do that same calculation in here. So you can say PRB bandwidth. So how much PRB bandwidth will be? So this times 12, right? So 180 kilohertz, 360 kilohertz, 720 kilohertz, 1440 kilohertz, which is also known as 1.44 megahertz, right? So they have, so here it is megahertz and megahertz. In our calculation, it is going to be 2800 only. Okay. Then next thing is the, so I hope everyone understand what is PRB. Very good. Now after PRB, we have a frame duration. Okay. Now what is a frame? Or in simple word, radio frame. Like PRB is a bundle of resource blocks. So it represents the framing in the frequency domain. So similar way, radio frame represents bundling of resources in time domain. So this is fixed 10 millisecond in all cases. This is same, and the same is the case with LT also. So this radio frame has come out as the same. So every radio frame has got 10 subframes. Each one of them has got 1 millisecond each. Okay. So this is same as per the standard. This is same as per the standard, and number of symbols per slot is also same. This is also a standard. So 14 symbols will make one slot. So this is also a same thing.